Now let's look at another demonstration of that same phenomenon, using this time a drink dispenser from Skylab. Now for this demonstration, I partially filled a dispenser with an orange drink so as to allow for a little turbulence to occur when it was rotated. Then, after I spun it along its long axis, the turbulence caused the kinetic energy to be transformed into heat energy, just as in the case of the antennas for Explorer 1. Now then, let's observe the videotaped results of the Skylab demonstration.
Now, we know that the minimum inertia axis of a long cylinder like this is along the axis of the cylinder. And the maximum inertia axes are either of the orthogonal axes, and it was found that if a body is spun about its minimum inertia axis, it will not stay spinning in that direction. If there's any energy loss mechanism available at all, it'll gradually lose a little bit of its energy and not only slow down its spin rate, but also begin to tumble until it finally stabilizes, spinning or tumbling about one of its maximum inertia axes. And that's the first thing that I'd like to demonstrate here. And this is much like our Explorer satellite looked some 15 years ago now. It may take me a couple of times to get it spinning just right. Then I'll want to get it spinning. There's a pretty good one. And I'll blow on it just to keep it in the field of view here. Very gently. And now it's just about stopped. And you can now begin to see that as it loses a little bit of energy, because I've got some water bubbles inside here, that sloshing around of the water inside will gradually absorb just a little bit of energy. And you can see now how this drinking device is beginning to tumble just a little bit. It's beginning to precess and spin, and not about its longitudinal axis where we started, but instead about an axis just slightly off to one side. I'm blowing just very gently right about the center of mass so as to not disturb it if I can. And now it's just about to do that. We'll give it a few more minutes here. I've done such a good job of spinning it precisely that it's going to take quite a while for the energy to be absorbed. Just a very gentle breath is all that's required to keep it floating and stable. But now you see it's almost converted to a tumble. Very little spinning, almost none of it about its longitudinal axis or the minimum inertia axis that I was describing a minute ago. I have to blow it back down into the middle of our picture here. Okay, perhaps that's enough. Now you can see that all of the energy that it had in excess available has been lost, rushing around on the inside, and it has slowed its tumble down so that the momentum has remained the same. Now, if you'd calculate the amount of momentum that it had in it to begin with and the amount that it has now, the angular momentum should be the same. But the energy has been reduced until it is just sufficient to give it this angular momentum.
Now that we've seen both the Explorer and Skylab demonstrations, let's analyze for just a moment the equations that explain precisely what it was that's happened. Now this is, of course, the equation we've been working with. Total energy equal the sum of kinetic, potential, and heat energies. The kinetic energy can be expressed, if we like, as 1/2 moment of inertia times its angular velocity squared, potential energy, and then Q is just the symbol I've used for the heat energy involved. Now, we also know that the angular momentum, L, can be expressed as the moment of inertia times the angular velocity, and then this inserted back up into the equation for kinetic energy, if we should wish to, giving us with this final equation, which I want to talk about for a moment. The total energy equal the sum of these three terms. Now, we know from the laws that we've just been looking at that the total energy in the system must have been conserved and therefore held a constant. Also, the total potential energy did not change, because the bodies that we were looking at, both our drinking dispenser and the Explorer satellite in orbit, maintained their same relative position above the surface of the Earth so that the potential energy was not changing. And then finally, our other law told us that the angular momentum did not change during this time. So the only thing that has been left to vary during the course of this changing and rotation is the amount of heat and the angular velocity. Well, now we know that as long as there is any turbulence, as there was, for example, in the drink dispenser and with the flopping antennas, the heat energy is going to increase during the time it was rotating. So that term had to increase. And the only way that this equation can be maintained in balance then is for the angular velocity omega to have decreased. And of course, that's exactly what we saw happen. The high spin rates, the drink bottle and the Explorer 1, did begin to slow down, and the rotation rate diminish. Now, the one other thing to keep in mind as omega decreased is that the angular momentum L must still have been kept a constant, so that when this went down, in order to hold the momentum constant, the moment of inertia I had to increase, which meant that the drink bottle and the satellite did not spin any longer about their minimum inertia axis, but instead began to tumble and spin about its maximum inertia axis. In fact, its final stable condition was a spin about its maximum inertia axis at the minimum velocity, which was consistent with providing the required amount of angular momentum, and one in which there was no longer any turbulence generated, so that Q could no longer increase.